What is the surface area of a sphere of radius a? You might be able to quote that the answer is 4 pi a squared. Perhaps you've memorized this at some point in your mathematics education, but why? Why is that the case? Now, the sphere has an implicit formula, x squared plus y squared plus z squared equal to a squared. But what we really want to do in this video is to come up with a parametric way to represent the sphere that naturally captures the geometry of the sphere. This is going to make our computations a lot easier. And a natural parameterization for the sphere is spherical coordinates. So let's take a quick review of that. Now, I've talked about spherical coordinates and integrating the spherical coordinates in previous videos, so I'll put the link down in the description to that if you want to check it out. The idea is you can describe any points by 3 different coordinates, a, phi, and theta. The a is the length from the origin out to the point. The phi is the angle between that line and the z-axis. And the theta is when you project that line down into the xy plane, it's the angle between that and the positive x-axis. And then if you play around with the trigonometry here, what you get is that x is equal to a sine phi sine theta, y is equal to a sine phi cos theta, and z is equal to a cosine of phi. Okay, so writing down my parameterization, well, it's exactly what we just said. R of phi and theta is going to have an I hat, a j hat, and a k hat, and each of these are the 3 things we just saw. I do want to note here, though, that a is a fixed value. It's the radius of this sphere. So a is not a parameter. It's not varying as you move around. So the only 2 parameters that I have to describe the surface of the sphere is the phi and the theta. If you were trying to talk about the entire region enclosed by the sphere, then you might allow a to range between 0 and some number as well. But that's not what we're doing. We're just talking about surface area. We're trying to parameterize just the surface, and you only need a phi and a theta to do that as the a is given. And I had to be careful to specify what the limits are on my 2 parameters. So phi is going between 0 and pi, and theta between 0 and 2 pi. The fact that phi just only went to pi was to sort of avoid double counting points. It's sort of a weird quirk of spherical geometry. Now, I want to compute the surface area. And the formula that we're going to use for this is the formula that we actually derived in the previous video. That is, we're going to use a surface area formula that is computed if we have a given parameterization. What we're integrating is the length of Ru cross Rv, where u and the v are the 2 different parameters. In our case, they're going to be R phi cross R theta, because phi and theta are the name of our parameters. So I need to go and compute out the integrand. I'm going to step away for just a moment because I'm going to fill up this whole page with formulas here. So I've stated my parameterization. The position function R of phi and theta is as we had it. The first thing I need to do is compute 2 different derivatives. So I'm going to do first the R phi. So this is the derivative of the position vector with respect to phi. And so I just haven't touched anything with theta, and I've just taken the derivative sine to become cosine. And likewise, the derivative of cosine to become negative sine. I'll do the exact same thing for theta. So now I am leaving anything to do with phi fixed. I'm taking the derivative of cosine and getting negative sine, the derivative of sine and getting cosine. And then for the k hat term where there is no theta, the derivative of a cosine phi with respect to theta is just 0. Next up, I have to take a cross product. Cross product is just the determinant, so I write I hat, j hat, k hat along the top. I write the 3 different components of R phi on the second line and the 3 components of R theta on the third line. This is a determinant, and I will trust you to be able to compute it out. I'm going to go quite fast through here, but feel free to pause and verify my calculations if you want. The only thing that was a little bit weird is in the k hat. I used the Pythagorean formula. Specifically, I used that cosine squared of theta plus sine squared of theta is equal to 1. That's how I simplified the k hat expression. Not done yet. I need to take the length of this particular vector, the length of R phi cross R theta, which is going to be the square root of the sum of the components squared. And again, it's just some messy expression, but a messy expression that can be simplified pretty quickly, actually. For example, you notice how there's this cos squared and the sine squared, but they have the same coefficient. They have a to the 4th sine to the 4th phi in front of both of them. So I can use Pythagoras here. This simplifies down to just being the a to the 4th sine to the 4th phi times 1. That's cos squared plus sine squared is 1. And then plus the final term. And then even here I can simplify because I have this sine to the 4th term, but sine to the 4th can be thought of as sine squared times sine squared. And then I'm going to have a sine squared plus cos squared thing with two identical terms, and that's also going to collapse. And so I just get a squared sine phi. You might be a little bit mad because you're like, hold on, square root of sine squared, can you just leave it? But for the phi values between 0 and pi, sine is always positive, so yes, I don't have to worry about that. So a squared sine phi. All right, so I'll return visually here, and we're trying to plug it into this formula, this surface area formula. The only thing I've done differently is that now instead of u and v, I've labeled it as phi and theta, as I know that's what I'm going to do. And likewise, I put in the limits of integration. I knew that my phi was going between 0 and pi, and my theta between 0 and 2 pi, so I plugged that in. I'll then plug in the integrand of a squared sine phi, and now it's just a computation. So I can integrate out my sine to get a negative cosine between 0 and pi. A squared comes out the front. This integrand just evaluates as 2, and then integrating 2 between 0 and 2 pi is just going to give me 4 pi times a squared. That is, we have computed out that the surface area of a sphere of radius a is 4 pi a squared. The result you may have known. So to do this computation, we've used the power first of spherical coordinates, which naturally captures the geometry of things like spheres very effectively. We parameterized using those spherical coordinates, and then we just plugged into the surface area formula for a parameterized surface, and it was just a bunch of evaluations and some trigonometric tricks of Pythagoras identity to be able to compute out the final answer of this 4 pi a squared.